Okay, so we are continuing on with our discussion of momentum. I don't like that there at all. And we're going to look at more detailed collisions, interactions that involve momentum. We're going to look at what we call inelastic elastic collisions, and we're going to end the lecture talking a bit about two-dimensional momentum problems. Okay, so the first kind of collisions that we're going to discuss here are actually basically things we've done before. I didn't put a label on it yet, and so here I'm going to put the label on it. A lot of the things that we're talking about before are what's known as inelastic. And inelastic collisions, well, the way you can identify an inelastic collision is that typically as a result of the collision, the objects stick together. Okay, so the examples that you see here are different examples of what inelastic collisions will be. Now, what it means physically for an inelastic collision is that, I want to jump ahead of myself here, no. What it means physically for an inelastic collision is that momentum is conserved in inelastic collisions. However, energy is not conserved. Okay, that's going to be different from elastic collisions that I'm going to talk about a little bit later in the lecture here. For elastic collisions, both the momentum and the energy are conserved in those things. And so the way you can solve those will be a little bit different because you can take into account this extra little tool here that's allowed energy conservation. All right, so we got a 1 kilogram box moving to the right, 3 meters per second. There's no friction here. If there's friction, we couldn't do any momentum problem. It's going to collide and stick to the 2 kilogram box, and afterwards the speed of the two boxes is going to be what? All right, so the answer here is going to be B. So what's happening here is this. If you want to characterize what the system momentum is here, okay, the initial momentum of our system here, and again, I need to get off my butt and figure out how to do these superscripts, subscripts. I did something wrong. I don't know. Whatever. The initial momentum here. Now there's two objects in our system. So the initial momentum of this system is going to be 1 kilogram times 3. That's the first block. The second term is going to be 2 kilograms times 0. Speed 0. Okay. Now it's important that you actually put that in there. It's something that you'll have to keep track of. 0 now, it may not be 0 later, right? So what's the final momentum going to be in this? Well, they stick together. And when they stick together, they move with a common velocity. So that means when I do my masses here, I'm going to do 1 plus 2, and then I have a final velocity here. Now, what's happening is we take a 1 kilogram block, and when it collides with a 2 kilogram block, you basically created, an object that now has 3 times the amount of mass. So it's not surprising that our speed ends up as exactly a third of what we originally had. Again, I mentioned last lecture there's a proportionality here that you can do a lot of times with these problems, and you can see how it works here. But your conservation of momentum allows you to set these two equal to each other, and you solve for a V final. That's how you get your 1 meter per second. Okay. Now, in this situation, we have both objects traveling towards each other. So the 1 kilogram is going to the right at 4, 2 kilograms going to the left at 2. They're going to collide and stick. Inelastic collision. Conservation momentum works here. The answer here is... Does a drum roll. 0. That was 0. Why? Well, let's look at it again. What is the initial momentum of this system here? We got the 1 kilogram block moving at 4 meters per second. We got our 2 kilogram block moving at -2 meters per second, right? Vector quantities, make sure you put negative signs in there. Well, you know what? Look at this. 0, right? The overall momentum of this system is 0. So if they're going to stick together, if they're going to collide, then we're going to look at the combined masses of these two things with some final velocity. But the system momentum is 0. So that means the velocity has to be 0. So these two things are going to hit. They have the same momentum, the two objects, just one's positive, one's negative. All right. Fantastic. All right, so in a similar vein, we're going to try to do that here. All right, so we have a 1,500 kilogram car rolling around at 2 meters per second. That's not too fast. And that's kind of fast. I don't know. What was that like? It's not quite 10 miles an hour. It's a little less than that. But anyway, you'd like to stop the car by firing a 10 kilogram blob of sticky clay. Okay, so I'm sure all of you have wanted to do something like this before. Now you're going to learn how to do it. So if you got enough sticky clay, like Play-Doh, you can do it with Play-Doh. I got enough Play-Doh in this house. I can do this 5 times over probably. But we're going to fire it. Now the thing is, this is an inelastic collision. But what's going on here is the total system momentum is 0. Right? Because at the end of it all, we don't want anything to move. So let's go ahead and look at how that's going to go. All right. So the system is the car and the blob of clay. Conservation of momentum tells us that in this isolated system, if we can characterize the initial and final momentums, they will be equal to each other. I can see already from the description of the problem that my final momentum is 0. Nothing will be moving at the end of this. And so when I look here, my initial momentum is going to be whatever the clay is doing. Oh, actually, that's the car. Subscript is the car here. And then this is what the blob is doing. And I'll set that equal to 0. Okay, so the 0 is the final momentum. And you're basically create a proportion out of this. Right? So look at this. The blob of clay, right, is 150 times less massive than the car. So guess what? You're going to have to throw this clay at 150 times the velocity of the car. Well, we'll do the math here, and we did that here. And so we get a negative 300 meters per second. Negative 300 meters per second, all right? So, we put the masses in here. The VC is this 2. Negative 300. Now, it's negative because it's just indicating that you have to obviously throw it opposite the direction of the car's motion. That's why the negative's there. But this number makes a lot of sense. So if you can manage to throw your blob of clay, your roughly 22 pounds of clay, at the speed at which a jet flies, like an airliner, then you can do this. Right? Okay, a little more complicated thing now. Now you really want to pay attention to this thing because this has some subtleties to it. And what I would really want you to get out of this example here is seeing the consistency in how we solve these problems. And so this problem is going to be a little bit more complicated, but if you can really pay attention to the system that we've developed, you'll see a consistency in what's being done, and then you'll see that that ultimately this is not too hard to solve. So we have 2 half-kilogram blocks of wood. They're 2 meters apart. You got a bullet that's fired. It goes through one of the blocks, exits out the other side, and then it hits the second block and it gets embedded in the block. So you want to make sure you're very clear about what your system is. So block 1, block 2, bullet. These are all the things that move. This is an inelastic collision. We know because we shred the first block of wood and then we embed in the second block of wood. No, we definitely are not conserving any energy here. We are conserving momentum only. And so what you want to do is you want to be able to specify the system's momentum at different points in time. So this problem is a little different for a couple reasons. One, we have more than 2 objects. We have 3 objects. And we have multiple events taking place here. Okay. So what you want to be able to do is for every instant in time that you want to characterize the system momentum, you need to add up 3 terms. The 3 terms correspond to block 1, block 2, and the bullet. So I've labeled them A, B, and C. Okay. So before anything gets hit, block A and block B do not move. Okay. So that means that their momentum is simply 0. And that means the bullet is the only one that actually has any of the momentum here, which it will transfer to the 2 blocks, as we'll see in a moment here. So I wrote in here mass of the bullet times the speed of the bullet. So that's the only term we have here. Now that quantity there, and by the way, I know that number, right? That's a number that we know. Let me just, we can write it in here. Okay, that's going to be 0.01 times 400, right? All right, so that's 4 Newton seconds, or whatever, or kilogram, anyway. That's the system momentum. So that will never change. So when I develop an expression for the momentum at any other time, ultimately it will add up to 4 Newton seconds. All right, so what happens? We hit the first block. We go right through it, and now we're looking at the situation where the bullet's still traveling, but now a lot slower now, okay? So our second block is moving, okay? Now we are given what the speed of that block is, so that's nice of them to do that. So we actually know that term there. And then we have the mass of the bullet and its new speed. Now, I don't even need to know that. Okay, anyway, I just wrote it out, but it looks like we don't even really need it. Anyway, let's go to when the second block gets hit. So when the second block gets hit, this is really important what we're looking at here. When the second block gets hit, and we're trying to characterize the system momentum, you can't forget about. Oh, I don't like that. I'm going to get rid of that. You can't forget about that first block. It still is moving. It will still possess some of the momentum of the system, and so you have to make sure that you include that. Even though that after the second block gets hit, you're kind of focused on that, but you got to not forget that momentum is still there. The second block and the bullet combine, so we're going to add their masses up, and they're going to move with some final speed. So what I can do here is I can set equal to each other any of these 2 quantities. I can do P1 equals P2, P1 equals P3, P2 equals P3, anything I want to. Well, I want to know what the speed of the second block is, so that means I'm going to do probably P1 and P3. Okay, I'm going to equate that. So I write out what that is, put the numbers in, math happens, and I get a speed that's around 2 meters per second. Okay, that's the common velocity of the block and the bullet in there. Now, by the way, it didn't ask me in this problem, but I could actually figure out how fast the bullet was going after it went through the first block. It wasn't asked for in the problem, but it's something that we could do. Ultimately, I didn't really need to characterize the momentum at the intermediate step, but I'm just doing it because you can, and if that's something you needed to do, then you can work that out. But this is a really good problem because it puts a little bit more complexity in the problem. But again, one of the things I really want you to get out of this is to see the consistency in how these problems are solved. You're always identifying your system. You're characterizing momentum at 2 different or more instances in time, and then you equate the 2, and then you solve for your unknown stuff. Okay. All right. Now, sort of the opposite of an inelastic collision would be an explosion. And so, this may look different, something exploding, falling, and coming apart, but from a physical standpoint, it's identical to an inelastic collision. It's just going backwards in time. Instead of things colliding and sticking together, things are already stuck together and then they fly apart. And, in explosions, they're still considered inelastic collisions. You would actually classify them as an inelastic collision, even though it's not technically a collision per se. But physically speaking, they are identical to each other. Now, because of the explosion, your energy is not conserved here. So again, that's why it falls under the inelastic collision thing. And what's nice about explosions is when you start the problem, if the object wasn't moving to begin with, your system momentum is 0. Okay. Of course, if it was moving before it exploded, there would be some initial momentum there. But anyway, let's look at some examples of this. Okay, so this is, very similar to the quick check question I had before this. So we're kind of doing the opposite here. We want things to fly apart, right? So we got our two boxes, 1 kilogram, 2 kilograms, and there's going to be some explosion that will make them fly apart. Maybe there's like a spring compressed between them. That could be something. Actually, if that was the case, then it would be an elastic collision, but whatever. So the answer here is going to be B. Okay, so the initial momentum of this system is 0. Right, nothing's moving to begin with. The block on the left moves to the left at 4 meters per second, so we would characterize its momentum as -4. That means the other block's got to be +4, which means it has to be moving at 2 meters per second. Okay, so makes sense. Bigger block, slower speed. Makes sense. Okay, so this is an explosion example as well. We got a 50 kilogram archer standing on frictionless ice, shoots a 100-gram arrow at a speed of 100 meters per second. We want to know what the recoil speed of the archer is. So the idea here is, the ice is effectively frictionless. So if you launch something, there's a recoil speed. You launch something, you are exerting a force on the arrow, which means the arrow exerts a force back on you, which causes you to move. Of course, the mass of the archer is significantly higher, so we would not expect this person to move as much. Now, before I even do this problem, we have two things in our system here. We got the archer, we got the arrow, and I keep mentioning this proportionality thing here. Well, it applies here as well. Apparently, the archer, right, is 500 times more massive than the arrow. So guess what? The archer is going to recoil at a speed that is 500 times less. So I'm guessing my answer at the end of all this is going to be 0.2. Okay, archer arrow. It's an explosion problem, and nothing was moving to begin with. So initial momentum 0. Final momentum is going to be, the momentum of the arrow and momentum of the person. I'm using P for the archer. And again, it's just proportionality. So you solve for VP, and it's negative because, again, you're indicating that you're going to move opposite the direction the arrow is going. It's true. And we do end up with 0.2 meters per second. So straightforward explosion problem. So this is a little more complicated explosion problem. Actually, not really. It looks pretty easy, honestly. But all right. Dan is gliding on a skateboard at 4 meters per second. So this is a little more complicated. So this is an explosion problem, but this is what I said earlier. Not all explosion problems necessarily start with a system momentum of 0. I mean, if the objects are at rest, completely fine. But if there is motion, so you can, obviously you can have something explode that moves, which Dan is apparently exploding off of his skateboard here. So, so there is a non-zero initial momentum. But what is true here is that before the explosion takes place, Dan and the skateboard are moving as a system. So we would characterize the initial momentum as the sum of their masses times their initial velocity. Now, there is two things in the system here. It's Dan and the skateboard. There are technically two terms. I just factored out, the initial velocity, so it looks like one term. But of course, it's two terms. And I know all those numbers, I believe. I have the mass of both, right? Okay. And we have the speed. So we know the initial momentum of this. It looks like it's 55 times 4. So 55 times 4, I believe, is 220. So 220 Newton seconds is apparently the overall system momentum here. Of course, we don't really ever need to know that number. You can just see it at what it is. The final momentum is going to be that when the skateboard's kicked off, the skateboard is going to fly forward at a speed. Right? So it's going 8 meters per second, and that's what Vs is going to be here. Vd, well, what we know is that Dan's probably going to go a little slower. Just a little slower. Honestly, you could, if the skateboard is massive enough or kicked hard enough, this actually could cause Dan to go backwards. But this is all being viewed from a reference frame that's on the ground. So I mean, in the reference frame with the skateboard, yeah, he's going backwards. That's kind of an interesting problem, actually. Anyway, yeah, so we got our 220 on the left there. We're solving for our speed of Dan, and we get 3.6 meters per second. So he because he kicked the skateboard forward, he's moving a little bit slower. A little bit slower. In fact, I just love these proportionality things, so I'm just gonna be bugging everybody with them. But the skateboard is 1/10 of Dan's mass, and the skateboard went twice as fast as Dan. So going twice as fast. Oh wait a minute, that doesn't work, doesn't it? Oh yeah, it does. It's 10% slower. Yeah. All right, Dan's 10% slower because the skateboard is 10% the mass. That stuff's cool. Anyway, but the math shows you that. But you can, the proportionality stuff's really cool. Yeah, 10% of Dan's mass, so he goes 10% slower. Nice stuff. Okay, let's go back to the PowerPoint. All right, the other type of collision are elastic collisions. Things will not stick in elastic collisions. In fact, what happens is when the objects collide, a compression might occur between the objects, but the energy will be conserved in that. So we imagine that there is just some spring potential energy going on between them, but that's going to allow a perfect transfer of kinetic energy. No energy is lost in deforming an object. No energy is lost as, say, thermal energy. No energy is lost in terms of light, sound, whatever. And so you'll know if you're dealing with elastic collisions because either you'll be told that, which is nice, or there's no indication that things are sticking together. Well, a harder thing to do is to look at the problem and sort of understand that there's no energy loss. You know, something that deforms permanently, there's energy loss. Okay, so things like that. Anyway, but you know, billiard balls are a good example of that. They are effectively perfectly elastic. Okay, so if they deform in any way, they usually return back to their shape. And you hear a sound though, right? If you hear two billiard balls clack together, well, there is technically energy dissipated there. It's probably not much, enough that you don't really need to consider that. But anyway, it's not perfect. But perfectly elastic means, yes, the energy is conserved. Okay. So, in the example that you see up here, okay, there is a ball moving. Ball 2's at rest. So there's a kinetic energy to start here. The kinetic energy is only in ball 1. Momentum with ball 1. And so that's the before picture. And if you look at the bottom here, we see our equations. This is our initial stuff right here. Initial momentum of the ball, initial kinetic energy of the ball. The balls collide, and one possible scenario, okay, is that, say, the balls now both move to the right at maybe different speeds. Now, just to be clear here, that's not necessarily what will happen in this situation. There's a lot of things that can happen. I mean, ball 1 can rebound and go backwards. It just really depends on how fast things are going and how much mass there is, which this is what we're going to be doing here to figure that out. So then afterwards, we can characterize the kinetic and the momentum of both balls here. Well, if you look at this, I mean, assuming you know the mass of the balls, which you should, and assuming you know the initial conditions, how fast the ball was moving, technically speaking, this equation is solvable. You can solve this equation because it's two variables, two variables and two equations to unknowns, so you can solve it. However, it's not fun, and I'm telling you that there's a math thing that's not fun, so it's really not fun apparently. Not fun to solve this system at all. And so you're never going to do it because we've already worked it out. Here it is. When you do solve that system, okay, and I know we have a lot of time during quarantine here, so maybe you want to do that. Go for it. But if you do solve that system, we end up with these expressions down here. Okay. What these are the initial velocity of ball 1 multiplied by these particular ratios of masses. Okay? So you do need to know what the input velocity is of number one. And obviously you have to know their masses. Now, one thing that you have to do, you have to be very good about doing here. One thing you have to be very good about here is labeling things. Be very clear about what 1 is and what 2 is. And at least in this situation, it's going to be easy. 1 was the thing that moved to begin with. Number 2 was the one that was at rest. Okay, so when I see students do this, probably the number one thing that I see mixed up is they mix up the masses. Okay, the one that was moving, they call that M2. And if you do that, you're going to get messed up here. Okay. Now, another thing about this that is extremely important to remember, okay, extremely important to remember is this. Ball 2 needs to be at rest. If ball 2 is not at rest, you cannot use these equations, because guess what? Let's go back to what we had before. Okay, so what we had before is this. If ball 2 did move to begin with, there could be an extra term on this side, which would make this even more challenging to solve. That's a real nightmare, okay? But we got a way around that too. I'll show you that in a moment. All right, so, come on. All right, so anyway, there's the equations. Okay, you got another velocity of ball 1. You got to make sure you identify the correct mass for 1 and the correct mass for 2. And ball 2 has to be at rest. Will you remember that? Probably not. But should you? Probably yes. But I just see it a lot, so just be really clear about whether it's moving or not. Now, if it doesn't move, wait, no. If it does, wait, let me just keep going here. I'm going off tangent here. All right, so let's actually analyze these equations before I start talking about letting ball 2 move, right? Ignore that. Okay. We have a new textbook this semester. I didn't update a lot of the labels in here. All right. So one of the things I'm gonna do is to really help you understand these equations. We're gonna look at a couple different, three different scenarios of what happens here. And this is really great because this is really going to drive home the conceptual understanding of what's going on. Because you look at those equations and they look so odd, but there's a lot of meaning behind this. So the first example that we're going to look at is, what if the balls have the exact same mass? So this is very similar to billiard ball, right? The billiard balls have the same mass, and so when you have collisions that take place there, you can sort of see what happens. Well, if the masses of the balls are the same, okay, again, you got to look mathematically. What's going on up here, right? Mathematically, this is 0. You're subtracting the masses, that's 0. That means the final velocity of ball 1 will be 0. Okay, what about this equation right here? Well, if the masses are the same, then this entire ratio is 1. So what we see here, we see a complete perfect transfer of energy, right? We see ball 1 moving at a particular speed, ball 2 gets hit, ball 1 comes to complete rest, ball 2 continues to move on. All right, the other scenario is, what if ball number 1 is very massive, very, very massive compared to ball 2, right? So if ball 1 is very massive compared to ball 2, then again, we have to look at these equations up here, right? We look at these equations and we say, okay, what's going on? Well, if ball 1 is very, very massive compared to ball 2, then you can kind of ignore mass 2 here. And if you ignore mass 2, this ratio is 1. And what that's saying is that, technically speaking, that ball will slow down a little bit, but not much. If it's going to hit a little tiny thing, you're driving in your car and you hit a mosquito, this is what we're talking about here. Okay? The car is not going to slow down hardly at all. Same thing. If you hit a little tiny mass, that's not going to slow down the ball. It technically does, but it basically doesn't. All right. What about the other ratio here? Well, if mass 1 is very, very big compared to mass 2, then again, you can ignore mass 2. That allows you to cancel out mass 1 in the equation, and you end up with a final velocity for ball 2 being exactly 2 times the velocity of ball 1. So that seems crazy, right? Because this ball that's coming in is really not going to have its motion changed at all. I mean, very, very, very little. But what it's doing is it makes ball 2 bounce off, and it will travel at double the speed of ball 1. And so initially you might think, well, that seems weird. I mean, I could imagine that when you hit it, maybe the ball goes at the same speed as ball 1. But double the speed seems strange. And there's actually a really interesting way to understand why this takes place. All right, so try to follow me here in my logic. Let's get in a different reference frame. Okay, let's actually get into the reference frame of a ball 1. If you're in the reference frame of ball 1, okay, so when we say you're in the reference frame of ball 1, that means when you look at it, it doesn't appear like it's moving. Okay, it looks like the other ball is moving, right? So if we're in the reference frame of ball 1, then what we are going to see is we're going to see ball 2 moving to the left at the speed of the reference frame, right? At the speed of V1. And so then it hits that and it rebounds off. Okay, now that scenario is actually completely identical to you throwing a ball against the wall and having it rebound off. And if you remember, this is the whole Super Bowl stuff that we talked about in the previous lecture. But if you are in that reference frame, what did we learn? We learned that the change in the momentum of something that rebounds off of something, okay, this is your change in P, that's equal to 2mv. It's 2mv because you have your initial speed going in and you have your final speed coming out. And when you add those two up, because you're doing minus the initial momentum, but that velocity is now negative, so you're going to get a change of 2mv. And if I just rearrange things here, you can see that you can just basically treat this as if the velocity got doubled. So this scenario where a massive ball, hits the stationary object that's very small, and then the velocity goes twice. Initially you think, well, that seems really crazy. But then when you just physically, you create you transform this physically into an equivalent situation. You throw a ball against the wall. The change in momentum is 2mv. The ball's velocity is going in one direction, bounces off and goes in the other direction. So this is surprising, but when you think about it from a different perspective, it actually does make a little bit of sense. It seems a little counterintuitive, but it's not. That's cool. That is very cool, actually. So anyway, that's the reasoning for that. All right, the last scenario. You can probably guess what we're gonna do here. What if ball 1, okay, is very, very small compared to ball 2, right? Again, you got to look at the equations, right? Here's the equation up here. If you make ball 1 very small, then you cancel out m1. It's like, when I say cancel out, you're not actually canceling out, because mathematically that's abhorrent. Don't do that. You can't do that, right? What I'm saying is that it's so small that when you subtract or add, you effectively still get this stuff here. So you are ignoring it. You're not canceling out. I shouldn't say that. That sounds bad. Anyway, what you get from velocity of ball 1 is a -1. This ratio becomes -1 if m1 is very, very small. And so what that says is whatever the incoming velocity is, the ball will bounce off and go the other direction, okay, with the same speed. And then if you do this for the second one, okay, again, m1 is effectively non-existent here. So what you have is, again, I'm not canceling out. I'm just saying you can ignore these factors here. So m1 over m2, well, you really just you're ignoring this thing, actually. You're ignoring that thing. Anyway, the ratio of m1 over m2 is tiny. Tiny, tiny, tiny. So effectively, ball 2 doesn't move. And, if you stop and think about this a bit, this scenario here is identical to the previous one. It's just a different ball. But the change in momentum is the same here. It's 2mv. So, all right. So that's just a nice, those are basically the 3 scenarios you would ever have. I mean, in terms of physical behavior. Obviously, you got to plug numbers in to get, this stuff. But, all right. What's next? I have no idea. Okay. Oh, okay. So you're going to love this because it's hard. You're going to love this because it's hard. But it's not that bad. It's right. You're learning physics. So it's going to be hard until you learn it. All right. What if ball 2 is not at rest? What if ball 2 is not at rest? Well, you might remember back in chapter 3, I spent half the lecture discussing reference frames, okay? If both of your balls move, you can simply put yourself into the reference frame of ball 2, and then boom, magically ball 2's at rest. Now that's going to mean you have to alter the velocity of 1, okay? Do I have a picture of that? Yeah, here we go. All right. So we got these two masses, right? And you see the speeds, right? See the speeds of the masses. We want to know what the final velocity of these balls are. Okay, you can't do this yet. You can't use those equations that we had because it requires one of the balls. It doesn't have to be ball 2. I mean, you can label balls anything you want. The one on the left can be ball 2 for all you care. One of them has to not move. Okay, if you have them both move, then good luck solving that system of equations. That's gonna be a nightmare to do. But here's the trick. The trick is, let's get into the reference frame of ball 2 now. Now, if you remember when we talked about relative velocities, when objects move toward each other, it will give the impression that each ball moves faster. And you effectively will add together their velocities, okay? So, according to ball 1, if you are in the reference frame of ball 1, of course, you would think it's stationary because you're just stationary right next to it. And ball 2 would look like it's moving at 5 meters per second. Okay, likewise, if you're in the reference frame of ball 2, it's going to give the appearance that ball 1 is moving toward it at 5 meters per second. You simply add those velocities up. So this problem is effectively identical, okay? So what I'm going to do here is this. Now, this is a negative here, right? That's technically a negative. So what I'm going to do is I'm going to add 3 to these velocities. That is the transformation into reference frames. And so when I do that, now the problem becomes this. Ball 1 is now moving to the left at 5 meters per second. All right, 5 meters per second. And now ball 2 is at rest. Okay, now you can go and use those original equations. Whoa, that's not what I want to do. Now you can go and use those original equations. Now, guess what though? When you use those equations, when you go and use those equations, the velocities that you will get out of those two equations will be the velocities in this new reference frame. So guess what you're going to have to do? You had to add 3 to get into this new reference frame. Well, you're going to have to then subtract 3 to get back to the ground frame. So at the end of all this, you solve this thing here, and at the very end, whatever speeds you get, you will subtract 3 then. And then on both, and then there you go, then you'll get back. Okay, so let's look at examples. Let's just get into that. Anyway, okay, so here's the first step. 3 meters per second, we're adding these to these velocities, right? So this is the ground frame on the left here, on the right. Now I can't believe I did that. Anyway, on the right hand side is we transformed into the ball 2's frame. So we got 5 and 0 now, right? Then we use the equations, we transform them, we get a 1.7 and a 6.7. They rounded up, I didn't round up. And then since we added 3 here over here, we subtract 3. And we get our final speeds now. So that allows us to solve that system, that original system, in a much more easier fashion. And all of these problems are done in this manner. Okay, all of them are done in this manner, and you only ever have 2 problems. You only ever have 2 objects. You put a third object in there, and you can imagine that system gets even more nightmarish. So we'll never have more than 2 objects in elastic collisions. If you do, then you gotta be utilizing the. You gotta utilize some pretty high power math tools called linear algebra. And that allows you to solve those in a much easier fashion. But you don't know anything about linear algebra right now. Or at least you should. I don't know, whatever. All right, let's do an example. So in this example here, we have a situation where ball 2 is at rest, and then we're going to let it move. So let's look at this. All right. So in the first example, we have a 2 kilogram ball going to the right, 5 kilogram ball going. 3 kilogram balls at rest. One of the balls is at rest. That's ball 2. So I've labeled it up here. See that? 3 kilograms is ball 2. Okay. If one is at rest, that's ball 2. Ball 1 is moving to the right at 5 meters per second. So that is a positive 5. If it said left, make sure you put a negative sign in there. All right. I put in my masses, put in my initial velocity. We end up with a negative 4 and a 4. No, we don't. We end up with a negative 1 and a 4. Okay. So that means the 2 kilogram ball rebounded. It's going backwards now a little bit, a little slower. A lot slower, actually. And then the other ball is moving at this speed. So here's what's interesting about this result here. The masses of these two balls, very similar to each other. If they had the same mass, then this velocity would not be negative 1, it would be 0, and the other velocity would be 5. But guess what? Because ball 1 is a little less massive, we see that we are close to that answer. Okay? This second ball doesn't go 5, it goes a little bit slower, and then we see that instead of stopping, this ball is slowed down significantly and goes backwards a little bit. So that actually makes a lot of sense. If you actually think about those scenarios, this is conceptually very clear. Okay, so now, what if the resultant velocities of the two, we want to know what the velocities of the two balls are. The second ball is moving at 4 meters per second to the left. So now that ball is not stationary. Now it's moving toward the other ball. Okay, and so what you'd have to do here is, and you can see my little picture that I have on the right there. So here is the original scenario. We got the 5 going. We got 5 meters to the right, 4 meters to the left. When we transform it, remember what you do here. You add them up, the velocities, the absolute values. Add them up. So it's equivalent to saying that ball, the 2 kilogram ball moves at 9 meters per second, and the 3 kilogram ball is at rest. I use my equations. I put a 9 in there now. I get my velocities, but now since I added 4, I have to now subtract 4. So if I subtract 4, we end up with these new speeds here. All right. So again, look for the consistency. These problems are always solved the same way. You transform the velocity to make one of the balls, ball 2, so to speak, whatever, not move. So you're always adding or subtracting something. You use the equations, then you do the opposite operation. Okay. That's a lot. It's not too hard, I guess. All right, what is this? I don't remember this. I mean, this is not that important, I guess. This just explains basic propulsion. Heat up gas, shoot it out the back. Momentum transfer. I don't really have much to say about this, actually. Move on. Last topic. Two-dimensional momentum. So everything we've done up to this point, technically vectors, only dealt in one dimension. So you didn't really see vectors other than we put negative signs on things. But, of course, the reality of situations are that momentum can be conserved in 2 or 3 dimensions. So I'm going to do the 2-dimensional example. Of course, if you want to do 3 dimensions, you just continue on and add an additional equation. But this does require you to do a lot of vector decomposition. Okay, so let me ask you a question to start off with. A cart is rolling at 5 meters per second. A heavy lead weight is suspended by a thread beneath the cart. Suddenly the thread breaks and the weight falls. Immediately afterward, the speed of the cart is what? So, well, if you said less than 5, then you would be wrong. I'm sorry. It is still, it's still 5, right? So this is incorporating our two-dimensional motion here, okay? I mean, what you might think, maybe, well, if you drop the weight, the cart weighs less, right? The cart weighs less, and so you actually might expect the cart to Well, actually, you'd think it'd speed up. Now I think about it, yeah. If you say, well, the lead weight drops, and so that would, that's less weight. So if it's less weight, you'd expect the car to go faster. Except guess what? When that lead weight drops, it's still going 5 meters per second. So if you're looking at X direction stuff, by dropping the weight, you've not changed the momentum in the X direction at all. The system. Okay, so the cart's not going to have any difference. What will happen though is now in the Y direction, the lead weight's going to start to increase its momentum. But then you have to include the Earth as part of the system, and again, we don't really do that. It's too complicated, unnecessary. We do energy for that. Anything that involves energy, anything that involves gravity, you should be using energy. Anything that involves gravity, you're not doing anything with momentum, unless you're doing like astrophysics, and which we will do a little bit later in the class. We do a little stuff on gravitation, orbits, things like that, and you'll see it at least once there. But if you're on Earth, no, you don't do that. Last problem. Okay. We have 2 balls of clay. All right. One's moving directly to the east, so it's moving to the right 2 meters per second. The other one is moving down and to the left, 30 degrees south of west. So I have a little picture here, so it's very clear what we're describing. Okay. So it's going 1 meters per second. Now, the system of the 2 balls of clay. So just like before, you're going to have a statement that is the initial momentum of the system and a statement that is the final momentum of the system. Except the only thing that's different here is you're going to break things into components. So what looks different, what you will notice that looks different, is that I have vector notation on everything. So that when I do my velocities, you should be writing out the I and j hat components of that. Right? So before they hit, the 20 gram ball of clay has a velocity that is simply 2 I hat, just moving to the right. When we look at the velocity of the 30 gram ball of clay, we see that its velocity is a -1 cosine 30 in I hat. So that would be, let me draw a picture here. The -1 cosine 30 is this component, okay? And then we have a -1 sine 30, which represents the object's y momentum, okay? Or y velocity. And of course, we multiply that. So the mass times the velocity vector is going to be the system momentum for that object, right? They're going to collide, right? They're going to collide and stick together. It's an inelastic collision. So because it's inelastic, we're not using those equations that we just did. Again, be very clear. Elastic collisions, you use those equations. Inelastic, you're just doing the stuff we've been doing before. But we do add up their masses, and they have some final velocity to them. So we equate the 2 momentums together. Oops. We equate the 2 momentums together, and we solve for V final. So what you are doing, just to be clear, because it looks like I may have skipped a step here, but you're taking this equation, and you're setting it equal to this equation. So to solve for V final, that means you're going to just basically take the first equation and you're going to divide by the sum of their masses, which is what you see down here. Okay, so this part here is the numerator, and the sum of their masses is the denominator here. And so you got to combine I hat and j hat components up, do all your math there. You should end up with your I hat component being about 0.28, your j hat component's -0.3. That is your velocity vector. That's not your speed though, because you got to combine the components back together. So this is, if you remember way back in kinematics, you do your Pythagorean theorem on this. You get an overall speed of 0.41. And, I drew a little picture here. My I hat component's positive, my j hat's negative. So what that means is when these things hit, apparently after they collide, they're going to move down and to the right. So that's what's going to happen is, you got this thing going to the right, you got this thing going down and to the left, but when they hit, they're going to stick together and they're going to move down like that. And so I drew a little picture so it's clear what my angle is. If I do an arc tangent there to get my angle, it's going to be the y component, okay, over the x component, and I get a 47-degree angle. So it's good. The combined blob of clay is going to be moving at 0.41 meters per second, and you could describe this as 47 degrees south of east. Right? 47 degrees south of east would be a good, or have a picture like I did, And the reason by the way, if it's not clear, the reason why I know that's the picture is because you look at the components. The x component is positive and the y component is negative, so we're pointing down in the fourth quadrant here. Whew. All right, I think I'm done. So let me stop my recording.